Hello seniors, hope you're doing fine during these days. Today we're going to see electronic assignment number 10, which is Convergent series and sums to infinity. Up to now, remember to make a quick review of what we were studying. We've seen patterns and sequences, and then we focused on two specific types of sequences, which are arithmetic sequences and geometric sequences. Arithmetic sequences were the ones in which we could find a common difference between the terms. For example, let's say 1, 3, 5, 7, 9, and so on, where there's a common difference of 2. And we've seen geometric sequences, which we say that are terms which have a common ratio, right? For example, 2, 4, 8, 16, 32, 64, and so on, where we have a common ratio, which means a common multiplier, right? In this case, the common ratio would be 2, right? Okay, we've also seen the definition of arithmetic and geometric series, which basically implies adding all of the terms of an arithmetic or geometric series. We've seen the formulas for both, okay? So, today we're going to see convergent series and sums to infinity. So the objective for today's class is this: determine the converging value of a convergent geometric sequence. Okay, so we're going to see what converging means. So let's start by doing this very short and interesting investigation. Imagine, it says, consider the following geometric series. Okay, we're going to see this in a second. But first of all, imagine you're in a room which is 5 meters long, and you decide to travel throughout the room by making the following following the following pattern. Imagine your first step, you go 2 meters, okay? 2 meters. For the second step, you do half of the previous step, so you just do 1 meter, okay? Let's say it's something like this, 1 meter. Then for the third step, you're going to do half of the previous, so this would be 1/2. So this kind of is half of 1 meter, and so on. Then you're going to do 0.25 meters, and so on. So the question is, do you think that this person, considering a 5 meter long room, will make it to the end, up to here? Do you think that if this person continues with these patterns of steps, do you think that person will reach the other end of the room? So we're going to analyze this together. This is what converging series is about, and you will be understanding this in a second. So imagine this situation, but into a numeric problem. So this is a geometric series, right? Because we have 2 plus 1 plus 0.5. We're always dividing by 2, and we're adding all of the terms. That's why we call it a geometric series, okay? So let's perform this investigation. It says, for number 1, find the common ratio R. In this case, how do we calculate the common ratio? To calculate the common ratio, remember, we had to divide the second term divided by the previous term, right? So in this case, it's 1 divided by 2, which is 0.5, right? Or 1/2, we could leave it as 1/2. Okay, so this is our common ratio. Then for part 2, it says, use your GDC to calculate the values of S of 10, S of 15, and S of 20. Okay, so if you remember from our formula booklet, the formula for the sum of geometric sequences is the following: U1 times R to the power of n minus 1, or we could use the other one since R is less than 1. This would be 1 minus R to the power of n divided by 1 minus R. If you remember this, let's see if I can find the formula booklet. In a second. if we go to the formula booklet, remember here, this is the formula we're applying, specifically this one, okay? So that's the formula for the sum. So first of all, we want to find S of 10. So we're going to calculate S of 10, which is, what is U1 in this case? U1 is 2, right? So 2 times 1 minus 0.5 to the power of 10 divided by 1 minus 0.5. If you do that in your calculator, you should get, let's see, you should get, let's do this quickly. This would be, you can do it in your calculator as well to follow the class. 2 power of 10 divided by 1 minus, divided by 1 minus 0.5. This gives us 3.996. I'm going to write it with all of the decimal places just for you to see something. Okay, so this is S of 10. It's almost 4, right? 3.996. Then let's calculate S of 15. S of 15, this would be exactly the same thing, but instead of having 10, we're going to have 15 as our n, right? So let me do the following. I'm going to put it like this. This is S of 15. So instead of this 10, we will get 15 here. So this would be, the answer for this would be S of 15 equals 3.9999. So you see that we get almost the same number, but it is closer to 4. But you see that it never reaches 4. Then if we try finding S of 20, we would get, this would be once again the same thing. Let me bring this. This would be here. S of 20, this would be 20 and to the power of 20. And if you do that in your calculator, you would get S of 20 equals 3.9999 and more nines, 9, 9, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Oh, 9, 6. Okay, so it's not 4 yet, but it's a number which is very close to 4. Okay? So you see that the difference between the sum of the first 10 terms, the sum of the first 15 terms, and the sum of the first 20 terms is almost nothing, right? It's almost the same number. So you see that these terms are, and this is what we call, they are converging to a value which, if you think about, is the number 4, right? All of the numbers are adding up to number 4. And if you try to understand why this occurs, imagine this series over here and try plugging in the rest of the values. You would see that this would be 2, then 1, then 0.5. I'm going to put it with the addition. 2 plus 1 plus 0.5 plus 0.25 plus 0.125 and so on. So you see that this would be then 0.06 612, 6125, I think, and so on. So you see that the numbers are getting very small each time, and that means that if we add smaller numbers each time, we would still be getting small differences between, in this case, S of 15 and S of 20, right? But we're adding very small numbers. That's why the difference is very small. And this is what we call converging series. So let's keep on doing this. Then it says write the full values you see on your GC screen. We already did that. Then if we do part 2 of this investigation, it says, do you notice any patterns? Why do you think this is happening? Okay, so this is what we explained, right? You see that the pattern is that we're almost reaching the number 4, but we're not getting to number 4. And this is happening because we're adding smaller and smaller numbers each time, okay? So let me see if I can get this. Okay, so this is a pattern. Each value is half of the previous term. I'm going to take this to the other class. I need to. Okay, so each value is half of the previous term. And then for number 3, it says, now use your GDC to calculate S of 50 for each series. Do you think your calculator is correct? So if you try calculating S of 50, try doing this with your calculator and you would see something. This is 2 times 1 minus 0.5 to the power of 50 divided by 1 minus 0.5. And if you do this in your calculator, you should get, let's see, you would probably get 4. Yes, if you do this in your calculator, you'll get the number 4. But do you think this is correct? Explain why or why not. And the answer is no. The problem is that the calculator doesn't have much memory. So the real value is something like 3.99999 and lots of 9s. And since the calculator cannot display all of the 9s, it just rounds up to 4. But this is not the right answer. It's actually 3.99999 and lots of 9s. And that'll be the result, okay? So that's not correct. See what I put? This is, no, it's not correct, as the GDC cannot display all the decimals. Okay, so I'm gonna put this here. Okay. So that's an introductory problem for you to understand what a converging series is. And you see that in order to get a converging series, and we're going to see the theory in a second, the condition is that the value of r should be a number between 0 and 1. So it must be a decreasing geometric series, okay, in order to have a converging series. So it says, for each of the series in the investigation, you should have noticed that the values S10, S15, and S20 are very close. This is because when a geometric series has a common ratio r less than 1, the difference between each term decreases, becomes closer to 0, as n increases. This means that as you add more terms, the value of the sum changes very little. The sum is actually approaching some constant value as n gets very large. We call geometric series such as this convergent series. So that's the definition of a convergent series. In the series 2, 1, 0.5 plus 0.25 and so on, you might suspect that the sum is approaching 4 as n gets very large. Okay, so now that you understand this, let's go back to this problem. Do you think this person would reach the other wall of the room if the room is 5 meters? The answer is no. Why? Because this series is converging to 4, as we saw here in the investigation, right? That means that it doesn't matter if this person makes infinite steps, the maximum distance that this person would travel would be 4 meters. Okay? So the answer is no. This person will never reach the other wall. And this is what we call a paradox. Okay? The hallway paradox, we may call this. Okay. Here it says, here's the paradox if you want to analyze this. Suppose you're walking down a 30-meter hallway. Every 10 seconds you walk half the distance to the end of the hallway. How long will it take for you to reach the end of the hallway? Okay, so it's the same problem, but with different values. So the person in this case will never reach the end of the hallway. Okay, then it says convergent series. The sum of terms of a geometric series, if you recall this from the previous classes, we write it this way, using this formula. And this is the demonstration of this last formula, which we need to see, okay? Which is sum of infinite terms of a convergent geometric sequence, okay? We're gonna see where this formula comes from. You see, it's very simple and easy. So it says, as n gets very large, you can say that n approaches infinity. that means n tends to infinity. That's how we interpret the arrow there. N tends to infinity. If the common ratio is less than 1, then as n approaches infinity, r to the power of n approaches 0. Why is that? Why do you think that r to the power of n approaches 0? Consider the following problem. Let's suppose that r, let me take this down a little bit. Let's say that r is 0.5, okay? And you see what will happen here. If we square 0.5, 0.5 square is 0.25. Then if we square this answer once again, we would get 0.0625. And then if we square, sorry, there's a mistake here. If we take this power to this number to the power of 10, we'll get an even smaller number, and so on. So as we approach, I think this should be, let me see, 0.5 cube. Yes, this is fine. So let me change this a little bit. If we do 0.5 cubed, we would get 0.5 cubed. We would get 0.125. Then 0.5 to the power of 4, we would get 0.0625. You see that as we're increasing the exponent of this common ratio, which is less than 1, the answer we're getting is smaller than the original term, and it's getting smaller each time. So if we, for example, do 0.5 to the power of, let's say, 100, you can do that in your calculator, and you'll see that you will get a very small number. I'm going to pick a smaller exponent just for you to understand this. 0.5 to the power of 10, this is a very small number. This is 0.000977. Okay, so it's a very small number. So if this exponent, if we take this to infinity, 0.5 to the power of infinity, that's a very big number. The result should give us 0, right? Because it's a very big number what we have in the exponent. And as these numbers are decreasing when the exponent increases, then if we take 0.5 to the power of infinity, we should get 0. That's why we have this. As r to the power of n approaches 0, as n tends to infinity, r to the power of n tends to 0. That's why, if we go back to this formula, you would see that instead of writing r to the power of n, we're writing 0, because we're approaching n to infinity. So we get this. If we do the distributive, we'll get u1 over 1 minus r. And this is the formula for convergent series, for the sum of infinite terms of a convergent series. So it says, we can write this as, we're going to learn this limit notation further on this year when we talk about limits and derivatives, but this means the limit of this equation when n approaches infinity is this turns out to be 0, because r to the power of a very big number tends to 0 if r is less than 1. So this equals u1 over 1 minus r, which is the same thing we got here. So the sum of infinite terms of an infinite geometric series is given by this. u1, the first term, divided by 1 minus r, where r is a common ratio that, remember, should always be a value less than 1 and greater than 0. Okay? So don't forget that, people. This is where the formula comes from. Then it says, and here's a very important thing you should remember. Important. This is only true for geometric series and only when the absolute value of the common ratio is less than 1. Remember, if the common ratio is less than 1, the absolute value, that means that the common ratio should be between -1 and 1. And the very important clarification here, only for geometric series with this condition. This does not apply for an arithmetic series in any case, okay? Then it says, this means that as n gets very large, it approximates infinity, the value of the series is approaching u1 over 1 minus r. The series is converging to the value u1 over 1 minus r. We write this as s of infinity and call it the sum to infinity. Here it says, we say the limit of, okay, so this is how we read this expression over here. So it says, for a geometric series with an absolute value of r less than 1, the sum to infinity is given by this equation, which, if you see, is the same equation we have in our formula booklet. And here you have the condition. It's only applicable if the absolute value of the common ratio is less than 1. So remember that. Okay, let's see some examples to see how this applies. This is very easy, people. It's just applying a formula. It says, for the series 18, 6, 2, and so on, find s of 10, s of 15, and s of infinity. So once again, we're going to calculate each of these terms. S of 10, if we're asked to find s of 10 and s of 15, we do not use this formula. This formula is only valid for s of infinity. So we should go back to the other formula we've seen, which is this one, okay? So by applying that formula, first of all, let's identify u1. In this case, u1 would be 18. And the common ratio, well, we should first determine if this is an arithmetic or geometric series. But if we're asked to find the sum up to infinity, we can be sure that this is a geometric series, okay? So the common ratio in this case is 6 divided by 18, which gives us 1/3. 1/3. It's better if you leave it as a fraction and not as a decimal, because 1/3 is 0.33333, and you would have to round some decimals if you're using decimal notation. Okay, so s of 10. By applying the old formula, which is this one over here, u1 1 minus r to the power of n divided by 1 minus r. We would get 18 times 1 minus 1/3 to the power of 10. Could write this using parentheses. Maybe we can make this a little bit bigger. There. Divided by 1 minus 1/3. And if you do this using your calculator, you should get, let's see, 18 times 1 minus 1/3 to the power of 10 over 1 minus 1/3. This is 26.9995. So you would probably already know that the converging value for this series is 27, right? So we're going to prove if that's correct. Okay, then we do the same thing for to calculate S15, the sum of the first 15 terms. I'm going to change these numbers a little bit. This would be 15. So this is 15 over here, 15 and 15. If you do that in your calculator, you should get a different number, which would be 15 here. This gives us 26.999998. So it's almost 27, but it's not 27, okay? And finally, we want to calculate S of infinity, which, remember the formula, which is the new one we see today, which is this one. So I'm going to write it here. S of infinity is u1 divided by u1 divided by 1 minus r. So if we apply that formula, this would be 18 over 1 minus 1/3. And this should give us exactly 27. If you do this using your calculator, you will get 18 divided by 1 minus 1/3. And this is exactly 27. So if we add infinite terms of this sequence, we're going to get as a result 27. Okay, so these are the results for this example. There you go. Let's see this example. This is the last one, yes. It says, the sum of the first three terms of a geometric series is 148, and the sum to infinity is 256. Find the first term and the common ratio of the series. Okay, so let's write down our information here. The sum of the first three terms of a geometric series is 148. That is, S of 3 equals 148. And we know that this is a geometric series, okay? So we know that we're going to be using this formula. U1 times 1 minus r to the power of n divided by 1 minus r. Then it says, and the sum to infinity is 256. So the second piece of information we're having is that the sum to infinity is 256. And if we remember the formula, the sum of infinity is u1 divided by 1 minus r. Okay, so with these two pieces of information, we need to find the first term, which is u1, and the common ratio, which is, in this case, r. Okay, so that's what we need to do. If we have S of 3, we can rewrite using this formula the following. We would say that S of 3, which is 148, equals u1, which we don't know, times 1 minus r, which we don't know, to the power of 3, because this is S of 3, divided by 1 minus r. We don't know r. So we see that we have two variables here, u1 and r. So we need a second equation to solve this. If I write the second equation, which we're going to write by using the second piece of information, the sum to infinity is 256. So 256 equals u1, which we don't know, divided by 1 minus r, which we also do not know. So you see that here we have two equations with two variables, u1 and r. How can we solve this without complicating us too much? You see the following. In the second equation, we know that 256 equals u1 over 1 minus r, right? And if we go to the first equation, you see that we could get this here. u1 over 1 minus r is the same thing I just circled there, right? So this should equal 256. So if you notice that, we could rewrite the first equation by saying 148 equals, instead of all the green part, we're going to write 256 times this part over here, which is 1 minus r cubed. And this is almost solved. Now we need to solve for r. Leave the r alone, okay? So we're going to start by dividing 148 divided by 256. This is equal to 1 minus r cubed. If you do this in your calculator, 148 divided by 256 gives us, I'm going to continue over here. This gives us 37 over 64. This equals 1 minus r cubed. So then we could take the r to the other side. This would be r cubed equals 1 minus 37 over 64, which is 1 minus, the answer is 27 over 64. And if we take the cubic root in both sides, we would do cubic root of r cubed equals a cubic root of 27 over 64. In this case, the cubic root must affect all. Cubic root, there you go. So r equals the cubic root of 27, this is 3, and the cubic root of 64 is 4, right? So if you do that, you can check that using your calculator. The cubic root of 27 over 64 is 3/4. So now we already have the common ratio, which is 3/4. And in order to find u1, we can plug in the value of r into this equation, for example, right? So we would say, I'm going to continue here, 256 equals u1, which we don't know, over 1 minus 3/4. And then we can solve for u1, and we would get that 256 times, this is the same as 256 equals u1 over 1/4. So this is the same as saying that u1 is 256 times 1/4. Yes, times 1/4, which is 64. So u1, the first term of this series, is 64. That's how we solve this problem. Okay? I hope this is clear enough. It's generally a very easy topic for students. It's just applying formula. But if you have any doubts, do not hesitate to ask this in the Google Classroom. See you, seniors. Have a nice day.